Hi, welcome to Working with Raster Data using Python session. This is Nawajish Noman, and with my colleague Hao Hu from Esri Redlands. So today we're going to talk about what you can do with raster in Python. After that, we're going to talk about what modules you have available in ArcPy to do that job, and then the centerpiece of all of this is Raster Objects. We'll talk about that. Then we'll switch to do some work, and we'll talk about how you can visualize and explore raster data, and followed by some raster data management and processing. Then we'll switch to our most interesting thing in JS, which is analysis. So we'll show you how you can do raster analysis using Python, and then finally we'll get to Numpy Array and how it can help you to do some custom analysis. So let's get started. What are the things you can do with raster in Python? You can visualize and explore the data. Even though people may visualize data in app, but we'll show you that you can do that in Python too. For any project, you have to do data pre-processing and sometimes batch processing and automate the workflow, so we'll show you how to go about that. Then we'll talk about how you manage your data. So data management is something that you can do. You can do raster analysis, as we mentioned earlier, and custom analysis. So do all these things, how do you get started? What kind of Python functionality we have in ArcGIS platform? In ArcGIS platform, we have a large, rich ecosystem. You access all this functionality through different APIs, and we have primarily two sets of API. The first one is ArcGIS API, which works with ArcGIS Enterprise in a server context, ArcGIS Online, and through this API, you actually perform your operation remotely on a server. On the other side, we have ArcPy. ArcPy you use primarily to work locally for your local processing and mostly used in ArcGIS Pro and ArcMap. Our focus today will be ArcPy. In ArcPy, we have many functionality, over 1,300 functionalities and tools to do different kind of work that you can do. If you look at the different groupings here, you can see that we have data management, location analytics, cartography, 3D, and exciting one, machine learning. All of these are packaged together in ArcPy. But here we're going to talk about the two key important things to us, which is raster analysis and imagery analysis. With raster analysis, you can do many kind of functionality like extraction, overlay, proximity analysis, hydrologic analysis, Map Algebra to do different kind of operation, fuzzy overlays. So the type of operation you can do using raster analysis, a huge collection. On the image analysis, you can do orthomapping, information extraction, like classification, and full motion imagery work. For both sides, you can do a lot of data management, raster data management. So where these functionalities are available? These functionalities are available in modules, because in Python, everything is kind of grouped together in modules. And our favorite two modules that we will work with here are Image Analyst module and Spatial Analyst module. We refer to them as IA and SA. So these are the modules where you will get all this functionality together. Like all modules, it must be imported. But how you import makes your life a little bit easier or difficult, because we will talk about it later that to do operations or analysis, we will use map algebraic expression. To keep the expression simpler, you may choose to import this module in certain way. Here is an example. You import ArcPy, and then from ArcPy, you import environment to control your analysis. But then from SA module or IA module, you go about importing all of them as from arcpy.sa import star or from arcpy.ia import star. That will let you write expression in a much simpler form, and we'll see how does that go. Now, as I said, the centerpiece of all of these things is raster object. Now, what is a raster object? The raster object is actually the representation of raster in Python. What does it mean? It means it actually presents all the things that you can get from a raster. And it could be a single band raster, it could be a multi-band raster, it could be a multi-dimensional raster. How you get this? This raster object can be created when you're actually executing a Map Algebra expression and you're getting an output. You can also point to an existing data set to do so. Or you are creating an empty raster and using raster info, that could be a raster object. Now, if you are creating an empty raster object or you are outputting from an expression, your raster will be temporary in nature and you have to persist it. It has many properties describing the data set. It has many methods that works with bands, multidimensional variable dimension and slices. It also have the read-write method to create a Numpy array from a raster or a raster from a Numpy array. Let's take a closer look at these properties and methods. Now, as I said, that you can get the raster object from 3 different ways, and the slide on the left-hand side describe that. But once you have the raster object, you can look at all its property, and you can see the properties are grouped in kind of certain category. You can see that some properties give you the location of the data set and where it is, what's its name, whether it's a read-only or not, whether it's a temporary or not, followed by what is the kind of data set it is, and what is the location, resolution, cell size, that kind of information. Some other properties gives you information about its value, maximum, minimum. Other properties give you information whether it's a multidimensional data and what are the variables or the slices. More geeky type of properties give you the format, pixel type, compression type, those kind of information, sometimes which you need to do some, make some decision and do some work. On the method side, you have, of course, the save. You also have way to export image. Then you have a bunch of method to get or set your property and get raster band out of it. Then you have a set of properties to work with multidimensional variables and dimensions. And you have read and write to read a Numpy array from raster or create a raster from Numpy array. Now we talk about multidimension a lot, so let me focus on that a little bit. What is a multidimensional raster? It is a raster which may change over time or change over altitude. So it is actually a 3 or more dimensional raster. It's a hypercube. Like, of course, it has its x and y dimension, and it may have other dimension like time or depth or altitude. A multidimensional raster contains 1 or more variable which are individual cubes. And as I said, the cube can have time or depth, and each slice on this cube is a 2-dimensional array. What are the example of some multidimensional data set we have? We have mosaic data set, we have other raster data set like CRF, NetCDF, all those are example of multidimensional raster. Now that we know all about raster object, let's get to do some work. First, we're going to talk about how you can visualize and explore the data. You should not start any project without knowing your data, right? So, see what kind of functionality we have to visualize the raster. We have a function called renderer, which you can use to visualize your raster using the symbology that you want. But if you don't like what you look, you can go and use other appearances function to change it, right? Like stretch, or maybe use convolution. Or if you're looking at wind speed or ocean current, you may use vector field renderer. Once you look at it, you want to know a lot more about your raster dataset and how do you do that. you go to your properties and explore some information. Okay, is it integer or is it floating point? Is it multidimensional or not? How many bands we have? So you have methods, properties for that. If you want to know about the location of the raster, the resolution, and the area it's covering, you go and look for extent, width, height, or cell size, those kind of properties. Then there are other set of properties, as I said, that will give you information about the values, maximum, mean, standard deviation, and so on and so forth. But as I said, that no project is completed unless or started unless you can do some data management like clipping or masking. So we have many functions to do that. On the other hand, we also have a lot of geoprocessing tool in data management toolbox which you can also use for data management and processing. Now, sometimes you may have to do all of them at once, not one by one. So to get all the raster, you may use ArcPy.list raster to get to all the data and process it in a batch mode. As we mentioned that you get raster data from different directions, so what you do, sometimes you have to manage them nicely. If they are spatially segregated and have different file representing different area, you may want to present it as a seamless output. Or you have different time slices or depth slices for a multidimensional data, but you want to present as a whole. So you can use Mosaic to do that, and once you do it, Mosaic will give you a dynamic mosaic of imagery collection. It has a table, it has represent a raster data set, and it lives in geodatabase. There are two steps to go about it. You first create a mosaic data set and then add raster to a mosaic data set, and you have different ways to control the properties of this mosaic data set. There are other tools that you can use to actually work with your mosaic and make it better and perfect. Sometimes you don't want to physically collect everything, combine everything in a mosaic or merge or things like that. So what you do, you create a virtual collection. And to do that, you can use the RasterCollection class to do that. And once you define it, you can actually get some properties, and you can actually call some method to do some work. There are many methods that will give you some analytical result, like maximum, sum. However, you can also use the map method to apply any function and function chains that you can apply on that entire collection. Now, with that, I will hand over to my colleague Hao to show you ArcPy in action. Hao?
All right. Thank you, Norman. Let me switch the source. Okay, that's good. In the first demo, I'm going to talk about raster data exploration, visualization, and preprocessing. So I'm going to cover how to read raster, visualize raster data, show you some properties and methods of Raster Object, and show you some raster data preprocessing, how to save raster data, and finally batch processing with raster data. I'm going to do the demo in ArcGIS notebook environment. So for those of you who are not familiar with ArcGIS notebook, it is an environment built on top of Jupyter notebook. So with this ArcGIS notebook, you can write your code, interact with your data, perform your analysis, and immediately view your result. Okay, and in terms of the experience, if you're already familiar with Jupyter Notebook, there's no major difference. Like you see the menu, the button here, and the type of cells. So pretty much, if you already know Jupyter Notebook, you should feel comfortable working with ArcGIS Notebook. But one thing is different from the Jupyter Notebook is that you don't need a browser to open your notebook. As you can see, it has been well integrated into ArcGIS Pro, so you can just open your notebook with this catalog window. All right? Now let's take a look at the code. So the first part, we need to import relevant modules. So here, import ArcPy. Also, as Norman mentioned, I also have to check out the extensions, Spatial Analyst and Image Analyst. And two most important modules I'm importing here is ArcPy SA and ArcPy.ia. Next, I'm going to set my environment workspace. By doing that, I don't need to specify the full path when I'm using my data. Now, the next line of code, I'm trying to read elevation raster data and assign it to a Raster object on the left-hand side. So as you can see, we're now creating a Raster object by reading from a raster data set. In Notebook, you can very easily visualize your raster data set by directly running the Raster object. So here, you can see the grayscale image of your elevation data, right? And also, you can put some color to it by using the render function. So here, by running this code, I'm using a color map. It's a pretty fine color map called elevation number 1. Now it looks much better, right? So in addition to visualize your raster data, you might also want to explore some properties of your raster data before you start analysis. So you can do that by directly access those Raster object properties, such as some statistics. Here, I'm showing the mean value of the elevation data. So you might be interested in knowing some other properties like the dimension of your raster. Here, the number of columns, number of rows, and also the number of band of your raster data, right? So there's also a method called getRasterInfo. So this method will return a RasterInfo object, and this object contains a compiled list of raster information. And let me quickly show you that. So here, I'm going to simply dump all this information as a JSON string. Before we take a close look, I'm just trying to make it look better by formatting it a little bit. So here we go. Here you can see some properties of your raster as well, like extend, right, and some pixel type, format, statistics. So you do not necessarily need to access raster data properties from this RasterInfo object, but this RasterInfo object can be used to create a new empty raster, which I will be talking about that with more details in the third demo. So just give you a heads up. Okay. As Norman mentioned in the slides, Raster object can also be created from a multidimensional raster. Let's do that, and I'm going to show you some properties and methods that are uniquely designed for our handle with multidimensional raster. Assuming I have this multidimensional raster, and I don't know what it is about, a very quick way to show that is by calling this property MDInfo. So let's print it out to see what it has. Similarly, I will use some JSON library to better format it, so it becomes more readable. From here, you can see some variables of your multidimensional data, like the salinity information, and also we can see other variables. Here has water surface elevation and water temperature, right? So if you're interested to see, for example, the dimension information of some specific variable like salinity, you can use a method like getDimensionNames and with the argument of your variable name. So here you can see additional dimensions of your variable in addition to the x and y. Okay, so we have done a quick exploration of your raster data, so visualization and some properties. Now I want to talk something about data pre-processing, because that's something you might want to do before your analysis. For example, I'm just quickly show you in the map view. This is your elevation data. Your study area might be in this red bounding box. You might want to clip your data first. In some other cases, you might also want to resample your data. So this two line of code is trying to do that. The clip tool and resample tool, as Norman mentioned in the data management slides, are the tools you need to use to clip your data and resample it to a different resolution. By running that, we can just quickly check, okay, our final output of the elevation data is in the desired cell size. And here I'm actually show you a little preview of Map Algebra, because as you can see, the output is on the left-hand side. So it is a temporary raster. In order to persist that temporary raster to the disk, you have to call the method save. So this line of code is to save the elevation final raster object into disk. Okay. And sometimes you might have multiple raster you need to pre-process. And I'm going to show you a tool, which is also mentioned by Noman. This tool is called List Rasters. Basically, this tool allows you to list raster data in a single workspace. So how to use that tool? First, let's change my workspace to this directory. We're going to first use this function with no arguments. Basically, it will list all the raster data in that workspace. And this function can actually take two arguments. The first argument is called wildcard. Basically, it will allow you to do some string matching. For example, you want to only list rasters with a name start with E, so you can do that, and then you'll only see like a subset of your raster data. The second parameter of the list raster is raster type. For example, if you are only interested in list the grid type of your data, you can do this. Then you'll only see the data with the grid format. All right, so with this function, you can simply put your preprocessing step in a for loop. So here, I'm going to do some preprocessing for my elevation and land use data, and I'm going to use those data to as an analysis input for my second demo. Okay, let's see. All right, I'll switch to Noman.
Thank you, Hao. I guess, you saw how ArcPy can be easily used to do some visualization and some pre-processing, and the expression that you have seen are pretty simple. Now that you have done this work, we want to go to analysis. How do you do raster analysis? You write map algebra expression. So what is a map algebra expression? It's a very simple but very powerful algebraic expression that lets you execute tool, operators, and function working with rasters and features also. Now it comprises of like input data, your operator, tools, or function, whatever you are using, and the parameters that goes with it, and the output, of course. Now, the one interesting thing about map algebra expression is a distinctive feature is the output is on the left-hand side, and all the other thing like tool and parameters, everything else on the right-hand side. The strength is in you can create a complex expression, and all these tools and operator are available in Spatial Analyst and Image Analyst module. To control your analysis, you can actually call the GP environment by calling arcpy.env and then specify your environment. Now, what kind of tools and functions are available to you? All the tools you see in Image Analyst Toolbox or Spatial Analyst Toolbox are available to you. In addition to that, there are many functions that are available in IA and SA modules. However, in order to use most of it, you have to check out Spatial Analyst or Image Analyst license. You can also use any other geoprocessing tool. Every tool has its unique parameter set. Some are required, some are optional. You have to be careful about it. And some of these parameters could be number, strings, and objects. So you have to specify them accordingly. If you take a closer look at a slope tool, and you will see your input and output and all the parameter. And if you look at the corresponding ArcPy signature and an example, you'll see all the input and parameters are on the right-hand side, whereas the output O is on the left-hand side. As we said that you can use operators. So what are operators? All those mathematical operators that let you add to raster or do something. So those are operators. And many operators are available in IA and SA module. Now you can actually specify them and then write a simple expression to do what you want to do. The problem is that Python needs to know that you are working with raster as opposed to number or string. And how do we do that? You actually specify a raster as a raster using Raster Object. So you cast it as a raster. And after you do that, you can actually run any kind of operator and do your work. Now, You can also combine a raster with a number, or you can actually take a raster object output and put it in another expression to do your further work. Now the output, as we say, is a raster object which is temporary in nature, which means you have to save it to make it permanent. Here is an example where creating my slope output and then saving it so that I don't lose it. We also mentioned that the power in Map Algebra is creating complex expression, so you can actually combine many tools, operators, and functions. Now you can use the one output to another one, we said that also, but most important thing to take away from here is if you are doing some kind of local operations or operator which are cell-by-cell basis, you can actually string them all together, and when you do that and execute, they work in one shot, which makes it more performant. Some parameters or tool have complex parameter. We call them complex parameter or complex control in the UI, and we have corresponding classes in ArcPy. They have many parameters. You can actually create them and define those parameters, and finally you can query them. And if you like the value, or if you need to modify the value, or if you're doing some kind of sensitivity analysis, you need to change it incrementally, you can do that also and keep using this object in your expression. Not all operation is done using raster. Some require vector, and some also require some vector analysis. So in your Map Algebra expression, you can actually combine vector and raster together, write a complex expression. And here is an example where I'm actually converting a raster to polyline and then doing a buffer around it. And we also use £sign for the intermediate data so that it is managed by the system. You don't have to do anything with it. With that, I'll hand over to How to see some analysis with ArcPy.
Right. Thank you, Norman. So before I start on demo 2, I want to quickly mention that in the first demo last part, you might see an error, right? When I try to do the batch processing, it turns out that I just have the output with the same name, so I quickly fixed that by rename the output. Okay, so let's start on the second demo. So in this demo, I'm going to focus on raster data analysis, and I will use a simple suitability model that identifies the best habitat to set aside for bobcat as a case study. The reason why I'm using this case study is that I consider this case study as a representative case study which covers different pieces of raster analysis, so I hope it will help you better understand raster analysis. So first, very briefly, what is suitability model in case you have never heard about this term? A suitability model identifies the best locations to site things such as a new shopping center, a housing development, or ski area, or it identifies the best areas to set aside for things such as parks, bobcat, habitat, or for flood control. So in our simple bobcat example, our goal is to identify the best areas to set aside for bobcat habitat. So I'm showing you this suitability modeling workflow. As you can see here, we're considering 3 main factors. So the first factor is slope. For bobcat, for safety reason, they prefer steeper over flatter slopes. And this slope data can be derived from elevation. And the second factor we are considering is the land use type. Bobcat prefer certain land use types such as forest more than others such as residential or commercial. And the last criterion we want to consider is distance to streams. So location closer to streams are more preferred. And as you can see, the distance to stream can be calculated from a stream network. And it does not make sense to directly add those slope, land use, and distance stream together because they're in different spatial unit and they're in different numeric scale. So you need to transfer them into a common scale, like from suitability score 1 to 10, and then assign each criteria a certain weight and compile them together to produce the final suitability map. So this is the simple suitability workflow I'm going to talk about. And now let's dive into the code. Still, we need to first import relevant modules. And in the first section, we're going to prepare the criterion of slope. So here I'm reading from the elevation data, and I'll have two map algebra expression here. So the first line is that I'm trying to convert the vertical unit of my elevation data from foot to meter. And then I'm going to call the slope tool, geoprocessing tool, to calculate the slope based on elevation data. Okay? And I can also use one simple map algebra expression to chain those two one together, which will produce me the same result. I want to emphasize on that for map algebra expression, so your input, your operators, so your tools you're calling are on the right-hand side of your equation, and on the left-hand side is the Raster Object output, and this Raster Object output is temporary. So for example here, if I close my notebook, this slope will not be persisted, okay? So we can take a quick view of this slope data we're preparing. Now, as I mentioned, we need to remap this slope to a common suitability scale so that it can be used with other criteria, right? So, for example, we have this remap table. We want to remap the slope with lower values, for example, 0 to 3 degrees to low suitability score 1. However, for slope that greater than 25 degrees, we will assign it with a large suitability score. The tool we're going to use to do that is called reclassify. And as you can see, somehow we need to represent this table information as a parameter to the reclassify tool. If you recall from Norman's slides, this is a complex parameter, right? And in Python, we have special classes to handle this. And in this case, the class we are going to use is called remap range. This class will take all these multiple arguments into to construct this one complex parameter and use that parameter as a single argument to the reclassify tool. So I'm going to run those two lines, and then it should just take a couple seconds. You should be able to see the transformed slope, and it has been added to the map. So here's how it looks like. All right. Let's go back to the demo, and the second part is to prepare the criterion of land use. It's pretty much very similar processing steps. You have the land use data, you have a remap table. You know that, for example, those developed regions, you want a lower suitability score. For the forest or like bare land, you want a high suitability score. So you will use a complex class here called remap value, different from the previous remap, remember the remap range complex class. This class will do value to value mapping instead of a range of value to value mapping. That's the only difference. So we're gonna run the land use part of the Raster analysis, okay? And now it should just take a couple seconds. You should be able to see the transformed land use suitability score. Okay, so for the third criterion, it's distance to stream. So unlike the elevation data and land use data, because we already pre-processed it in our first demo, clip that into our study area, in this case, the stream data has not been clipped. So I'm gonna briefly show you how the data looks like. I'm gonna turn off what we already have processed. Okay. Let's see. Now, you see the stream data, and our stud area is still this red bounding box. So we need a tool. In this case, we'll call this clip analysis tool. What it does is it clip our stream layer, feature layer, into the study area, and we are going to output it as a shapefile. Okay, and then we're calling a distance accumulation tool, which is Spatial Analyst tool, using the output from the clip analysis. So this tool will create a distance surface. So this surface with each pixel value representing the distance to the nearest stream. Okay, so you may be wondering, well, the first expression here, it does not look like map algebra, right? Yes, no, it's not Map Algebra expression because the output is on the right-hand side, and you don't have a left hand side output. So this is a non-Raster analysis operation. So you may wondering, okay, how is it possible if we want to chain those two operations together, like so it can be like a simple workflow? The answer is yes. And the trick to do that, as Norman mentioned in his slides, is to use the pound sign. So I'm going to quickly show you how that can be done. So instead of specify the full path of your output, of feature output, you just use this pound sign, and then use entire expression of your clip analysis as the argument to your distance accumulation analysis. So by this one simple Map Algebra expression, you do what these two lines do, and you don't need to keep track of your output because it has been handled by the system to a temporary output location. All right, so next we still have to remap the value to a common suitability score from 1 to 10. This time we're using the rescale by function tool because we want to do a continuous mapping. The last step of the suitability analysis is that now we get the transform the slope, transform the land use, transform the distance to stream. We're going to weight each criteria. So for example, we think land use is slightly more important than other two criteria. We assign a higher weight and then combine them together. Another Map Algebra expression will do the work, and we can quickly preview our final suitability map in the notebook. So here, the green value will represent location with higher suitability scores, and while the red value will represent location with lower suitability score. Okay, so lastly, in this demo, I want to talk about this analysis environment. Just think about that. If you want your output to be in a different cell size, or also you may want your output to be in a different coordinate system, a simple way to do that is to assign the proper properties to your environment attributes. So for example, by doing this, I'm specifying my output to be in cell size 100, and by doing this line of code, just specify my output coordinate system to be in this web mercator actually sphere. So, and then you just need to rerun what you have previously. So instead of showing you again the step by step, I'm combining all I just talked about, all these Raster analysis step I'm talking about in this one complex expression. So I'm going to first run it. So it will generate the suitability map, but with the consideration of the analysis environment you are specifying. So it should take maybe a couple seconds, and let's see. As you can see, we are chaining different tools and operators and complex class, and this pound sign way to chain feature analysis together into this one complex expression. Now we got the result. We can quickly view to double check the environment setting has been honored. So the cell size looks good, and the output map projection looks good. So with that, I'll hand back to Norman.
Thank you, Hao. So you have seen ArcPy in action doing raster analysis, which is great, isn't it? So you can use all the 1300 tools, 1300 plus tools, and all the functions and operator, all the thing we have to do your job, and you can string them together to solve some complex problem. But I can guarantee you at one point you'll say, I need to do something that you don't have tool for or function for. That happens occasionally. But there is a way to go about it. You can actually write your own custom function and custom tool to solve that problem. How do you do that? Now, in order to think about it, you have to think about the raster itself. Raster is nothing but a two-dimensional array. For multidimensional slice is a two-dimensional array. So if you can bring it to an array, then you can do operation with it. And this is where Numpy comes into the picture, right? It's an extension to the Python package. It can support large multidimensional array, single-dimensional array, and provide a library, huge library of operation that you can do with Numpy array. So how do we get this Numpy array? So there are two things you have to do. First, you have to get Numpy array from raster, and eventually you have to, after you do the processing, you have to take the Numpy array and have to create a raster out of it. So for that, you have two functions. One says Numpy array to raster, obvious, isn't it? The other one is raster to Numpy array, and you can do that. You can create your own raster. However, you don't have to call this function. You have actually a simpler way to go about it now. In Raster Object, we have two methods called read and write. Read, obviously, read the raster and give you a Numpy array. On the other hand, the write actually take a Numpy array and write cell value to a raster. You can use those. Sometimes the raster could be so big that you don't want to handle it, you cannot handle entirely in your memory. So you can actually use pixel block and pixel block collection to do that. A pixel block actually get array for a defined area within a raster, and once you define that pixel block, then you can use getData method to actually get the Numpy array. But how about processing the entire raster? How do you go about that? What you do is you actually create a pixel block collection which has a lot of pixels block, and then you go through your pixel block and do the operation. But if you don't want to deal with any of this Numpy array and want to visit all your raster cell one by one and do operation, you can use the new thing called raster cell Iterator, which actually visit each cell in Raster Object, using the row and column indices, and you can read and write cell value. It can iterate over multiple raster data set and perform operation on the same location. You can also just get the value directly from it. If you look at the syntax, it's pretty simple, and you have the arguments where you can specify multiple raster and also the padding, which how we'll explain everything in the next demo.
All right, thank you, Norman. Okay, so in the third demo, I'm going to talk about custom analysis with raster data. In particular, I'm going to show you how to use Raster Iterator to calculate the steepest downhill neighbor slope. So the outline is like I'm going to first briefly talk about how slope is calculated in ArcGIS, and then I'm going to bring up this custom slope algorithm based on steepest downhill neighbor. And then I'll show you how to use Raster Iterator, RCI, to calculate the custom slope. Lastly, I'm going to show you how to deploy the custom slope method as script 2 in ArcGIS Pro. All right, so first, very briefly about how slope algorithm is calculated in ArcGIS, so particularly the percent slope. Well, the essential idea is that the slope is calculated based on DEM, elevation data, and for each cell of your slope, you require all the 8 neighboring cell values. And here, the slope is determined by the rate of change in horizontal direction and vertical direction. Well, apparently this is not the only way to calculate the slope, and this slope might not be suitable for other analytical workflows. For example, in hydrology, there is a slope algorithm called steepest downhill slope. It's commonly used in drainage basin algorithms, but it uses different algorithm rather than our ArcGIS slope tool. So how it works, it picks the steepest of the 8 adjacent point slope value with the constraints that the point must be lower in elevation than the central point. To help you better understand, I'm showing you these 3 figures. So on the left is the DEM data, and for simplicity, we can consider the cell size is 1, and all the value here is the elevation value. So if we want to calculate the slope for the center cell here, we need to just go through all the 8 neighbors, right? So if the neighboring cell value has a higher elevation than center cell, we ignore that, and we calculate the slope. If you focus on like the lower middle point and the lower right cell here, you might think maybe the lower right one has the largest job, so it will generate the steepest downhill slope, but actually we're considering diagonal distance. So the true steepest slope here is the lower center point. So here we can use that lower center slope and assign to the center cell. That's how we calculate the steepest downhill slope. Apparently, that's a custom algorithm you have to implement yourself, right? So how are we going to do that? We're going to do that with Raster Iterator. So I'm going to go through you this code snippet, which will do the task. So first part is to import relevant modules, and I'm importing Mass, ArcPy, and this time I specifically import the raster and the raster iterator object from the ArcPy SA module. All right. Then I'm reading the DM data, my input DM data. I need the properties of the cell size because that will be used when I'm trying to calculate those diagonal distance. I also need to get the raster info. Remember in the demo one, I briefly mentioned about this raster info object can be used to create a new empty raster. So in this case, I'm getting the raster information from the DM data and use that raster information to create the temporary output our slope. By doing that, the output slope will have the same structure and the properties as the DM. But before we do that, I want some slightly change. For example, here I want to use a different pixel type of my output slope because I know that my input DM, the pixel type is integer. I don't want to keep that properties. I want a floating point pixel type for our slope. This is how can I do that. I just simply call the method set pixel type. And then I create that temporary slope raster. Now it comes to the central piece of the raster iterator. Constructing a raster iterator object with input DM and output new slope, and then I'm going to iterate over each cells. I have this slopes array predefined, which will store all the potential slope with the neighbors, and then I'm iterate through all the 8 neighbors using relative indices. Okay, I only care about the downhill slope, and then I'm calculating the slope value. And last, I need to assign the steepest slope to the output cell. So here I'm just getting the maximum value, right? So in case there is no slope here in this list, that will simply means all the neighboring cells has a higher value than the central cell. In that case, we don't do anything. The central slope will be handled as no data. Okay? After that, we need to process our new slope. Okay, so I'm gonna briefly run this code, and now we get the output. You can see this is the new slope, how it looks like. All right, so if you only deal with Python code, you might probably want to stop here. But if you want to run this custom slope as a other like geoprocessing tool, you might want to deploy it as a script tool. So how to do that? Well, the first step you need to do is to, under the toolbox, create a new item type called script. Okay, here, I'm already created one for you. Let's look at the properties here. In the General tab, of course, you need to specify the name of your script tool, and you need to specify the path to your script file. So this would be the actual Python script to execute all this algorithm. And then you don't want to hard code your input and output data, right? And as a script tool, you may want user to select their input and specify the location for your output. So those 2 parameters need to be handled as like parameters. And The last piece is that you need to do some minor adjustment of your code. The purpose is that first, you don't want this, as mentioned, input and output to be handled hard-coded way, and also you might add some logs while you're executing the tool, and that's all you need to do in terms of the minor adjustment. After that, you can open your script tool. Basically, it will look like other geoprocessing tools, and then you have the benefit that if you want to chain your custom tool with other system tools in a workflow like module builder, it will be quite easy to do so. So with that, I'm going to hand back to Norman.
Thank you, Hao. It was great, isn't it? So you can write your own custom function and solve all the different kind of problems that you are trying to solve with rasters. Now, when you write new tools or solve new tools, sometimes you're dealing with a large data and you may want to take advantage of all the processors you have on your computer and do multiprocessing. Now, you don't have to worry about doing this when you are using existing tools in the toolbox, because we have been doing that work for you. So there is no point of multiprocessing, do multiprocessing on a tool which is already doing multiprocessing. So this discussion is primarily geared toward your custom tools. Now, if you want to do multiprocessing, you have to think about what kind of operation you are doing. Is it a local operation or it is a focal operation? Local operation means you're operating on a cell-by-cell basis. Focal, you're doing your operation but looking with the surrounding cell, as Hao did for his slope computation, or looking at a zone or entire global raster. Now, of course, the parallel processing, parallelization, it cannot be done easily with a global, even though we have done our tool, but it requires a lot of effort. The simple parallelizing problems are local and focal, where you actually divide your raster and then send a different chunk to different processor, get the work done, and put it back together. When you do that, what do you get? You actually get some performance benefit. And take a look at this here. Here's an example where we have done this thing and we have got some performance benefit. Now, if you look at the first point on the graph, based on one processor, it's like pretty high, 450 seconds or so. Now, as you are going down on the right side, you see it's changing. So with two processors, it change much faster. Then as you go to third one, it's a little slower. Fourth one, 11 slower. As you go to fifth and sixth, it's kind of flattening up. So what does it really mean now? That even though you are distributing to multiple processors, you are not really getting additional benefit from it. So at that point, you probably don't want to use more than 4 or 5. So you have to be careful about that so that you don't use up all the resources unnecessarily without getting any benefit, because your overhead is now eating up your benefit of performance time. How do you do this thing? You can use the multiprocessing module in Python, and you can actually define all the tasks in a dictionary, and you create your pool of tasks, and then you map this task and send it to different processor to get the work done. That's how you can actually gain some performance. One of our colleagues, Neeraj Rajashekar, has written a blog about it. You can look for this and you can learn more about it, how to do this in your own workflow. With that, we're going to come to our end and talk about what we have seen in this session so far. You can do a lot of things with raster in ArcPy. You can visualize, explore, manage, analyze. You can also share the raster data using ArcPy. You will learn this kind of thing in another session. We did not touch that part. You can use ArcPy IA and SA module to do all this work with raster, though all the primary work with raster. You can also use tools from other area, but IA and SA is the primary place you go to work with raster. Raster Object is your kind of the centerpiece. This represents the entire raster, and it provides many useful properties and methods for single band, multi-band, and multidimensional raster. Map Algebra is a very simple but powerful way to perform raster analysis using tool, raster, and function. You can combine raster and vector analysis tool together in an expression as how has demonstrated already. Raster object output from Map Algebra expression is temporary by default. It's on the left hand side and it's temporary. So don't forget to save it if you need it. However, in order to use it in other operation, you don't need to save it. That's the benefit of using Map Algebra, because it's temporary in nature. It does the job and then it goes away. You don't have to manage it. We manage it for you. But the final one, you must save. And last but not the least, you can extend your analytical capability by writing custom code using Numpy, Raster Cell, Iterator, and all this thing, and do much richer analysis than you can do from out-of-the-box tool if you need to. With that, thank you very much for being with us in this session. Thanks.